go. Okay, solving systems graphically. Okay, so let's talk about what a system is. In this one, we're going to have two equations. Oops, sorry. Two equations. So a system is two or more equations. In grade 11 pre-cal, we're only going to deal with two equations. Like I said, I really enjoy solving systems with three. When you go into applied, I don't know, Carissa, maybe you can answer this. Have you guys done matrices yet, or will you do that in grade 12? Okay, yeah, it's like a box, and then there's a bunch of numbers in it and stuff like that. Okay. No, not yet. When you guys go on to further your education, if you take a linear algebra course, it's all about solving systems, but with 5 and 6 equations in it, and we usually use matrices to find them. So it does get, like, these are the baby steps, and then we won't talk about them, and then you'll go on to post-secondary, and if you do a linear algebra course, you'll do matrices, which will be solving systems of, like, 5 and 6. We start off with like 2, then you do 3, and then you do 4, and then all of a sudden you're in an 8 one, and you're like, I hate my life. Because matrices can be a little bit confusing, but they're a good way to use to solve. We're not going to use matrices for this, but just so you know where you're going. And in applied 12, you'll do basic matrices to solve systems. So if you're going into applied, then that's coming up in your future. Okay, we're going to do it algebraically and graphically. Those are the two ways we're going to do it. So 8.1 is graphically. Okay? Now, if we have two equations, so when we're solving it graphically, we're looking for where the graphs cross each other. So just like our invariant points that we just did, the solution for a system is a coordinate pair, okay? Because we're looking for where the two graphs end up intersecting. So an intercept is where you cross an axis, and intersect is where they cross each other, okay? So point of intersection. So the point of intersection is where the two graphs cross each other, and if it's a point, then that means it has a coordinate pair on it, okay? So intercept with a C is where you cross an axes. A point of intersect with an S, intersection, is where you cross, the two graphs cross each other. So just know that there's a difference there, okay? So to solve a system graphically, you must graph both equations on the same coordinate plane and see where they cross each other. Okay, so we're going to do some rough graphs here. These are linear quadratic. So what does linear mean? What kind of graph am I going to have? Straight line. And if I'm graphing a quadratic, I'm going to have a parabola. And I always say it in my head parabola, because then I know I'm spelling it correctly. So you can have quadratic systems or linear quadratic systems. So for this unit, you need to be able to, basic skills, you need to be able to graph a straight line, and you need to be able to graph a parabola. Okay? Those are your basic skills. And then you see where they cross, and that's the chapter 8 component of it. All right, so really cool. I'm just going to put a parabola on here. I know you're super excited. So in a linear quadratic system, how many solutions does that graph have, or that system have? Has 2. So it has a solution here and here, because those are the points at which the two graphs cross each other. You guys would agree? Yep. So this one has 2 solutions. And my highlighter looks a little wonky. It looks a little green, but it was supposed to be yellow. Okay, anybody want to guess how many solutions we can have in this one? So if I have a parabola and I have a linear, how many solutions can I have? One. It's going to cross in one spot. Ooh, and if you're coming into calculus, we'll talk about point of tangencies. And that's going to be super fun. So if you're planning on doing the calculus elective with me, then we get to talk about that. Do you know we're not doing calculus this year? Well, there were 7 who wanted it, but there was only 3 ready to take it next semester. Because you got to take your pre-cal before you do your calculus. So it was a very sad day for Miss Scallion.
Will you always keep it?
Yeah, I think so.
Are you gonna? Well, then you have to take pre-cal first semester next year.
True story. Yeah. True story. So we've got some options. No solutions. No solution, just one. So in the third option, so you can have 2 solutions, 1 solution, no solution. This one actually there's a 4th one as well that I didn't draw on there, but we'll do it in a second. So really, like in example 1, the linear quadratic, you've got an option of 2 where it intersects it twice, intersects it once. Another one might look kind of cool is if we did this and then it cut it like that. That's another option, like where it's only going to cross it once, right? So it can cross it once. I did it at a vertex. It doesn't happen. And then this one obviously is no solution. So if you were to guess what a quadratic system, what are my options here? 2, 1, and none, right? And then there's one more that we'll talk about. So 2, if you were to draw 2 parabolas that had 2 solutions, go, draw a picture. So you have 2 quadratics, so you got a parabola and a parabola. Draw me a picture that would represent 2 solutions. That's exciting. So that was mine. They actually are x-intercepts. It's pretty cool. But that could happen anywhere. Like it doesn't have to happen at x-intercepts. It's just, so as long as you have a graph that has 2 parabolas on it and they're crossing in 2 places, we're doing good. Okay, so now let's talk about one solution. What would that look like? For the record, I'm not getting very creative with I'm just always in quadrant 1 and quadrant 4. This might be a situation where they share a vertex, but one opens up, one opens down. Right? If they both open down, I guess one could be like really wide and one could be really skinny. Yeah, for sure. Another one might be, so this is what Madison said. She said, what if I had a really wide parabola? And then what if I had a really skinny parabola that both shared the same vertex? It's supposed to be an arrow. That's not a very good arrow. And then I was thinking, okay, what if we did this parabola that's going like this, and then we have one over here with a vertex, same width, does that, right? That could be another solution. So there's lots of options out there, whatever picture you choose to draw. Just know that one solution just means that it crosses once. And then the next one would be the no solutions. Where they won't touch at all. For the record, I need some marks deducted for my flat bottom parabola there. That is not a very good parabola. Somebody needs to deduct some marks. Now there's one other option. So this is 2 solutions. one solution, no solutions. I'm big on abbreviating words. And then the last one that we don't really talk about. So there's my axes. And if the graph lays right on top of it, so if both graphs are the exact same graph, how many solutions does this have? Infinite, because all the points match. So this one, if they lay directly on top of each other, if you have two graphs that are the exact same graph, this has infinite solutions. So can somebody explain to me why I don't have infinite solutions in linear quadratic? They're two different shapes. Like, it's the most obvious thing. I can't have a linear, because it's a straight line, have all the exact same points as a parabola, right? They're two different shapes. So the only place that infinite solutions can happen is when the shapes are the exact same. And yes, you can have a linear system. We're just not going to deal with them here. Okay, so you can have that. I'm going to be honest with you. We've dealt with those. Like, you have two whole numbers that add up to 14 and the reciprocals add to 2/9. That is a linear, well, that's not a linear, but you get the idea. Like, they're pretty simple systems. You guys have solved those a million times, okay? So now we're moving on to something quickly, something more a little bit complex. Okay, example 3, kind of silly. I don't know why I keep it in, but it's kind of important. So 2 divers start their dives at the same time. One diver jumps from a 1 meter springboard and the other jumps from a 3 meter springboard. So assuming that this is the height and this is the distance. Okay. Plot a graph that represents a situation with the height above water. Time elapsed. Jeez Louise. Time elapsed. I gotta read the whole question before I graph stuff. All right, so I know I have a 1 meter springboard and I have a 3 meter springboard. Okay, I know nothing about diving. Maybe some of you are more proficient in the swimming category than I am. But really what we have here, do you anticipate linear? Do you anticipate quadratic? We're diving off.
Quadratic.
Okay, so quadratic, so we're dealing with parabolas. We got 2 parabolas happening. How many solutions do you anticipate having?
1.
You want 1? Okay. So let's draw the situation as if we were going to have 1 solution. So that would be a situation where there's 1 solution, right? You guys would agree with me? Could we do it so that there's 2 solutions? Maybe. Could we do it where there's no solutions?
Yeah.
Yeah, we definitely could do it. So
You
if
could do 2 if, like, the one who jumps from 1 is, like, jumps very high.
so 1 and 3. So if we were to do 2 solutions, we could have this guy jump really, really high and this guy not so much. So there's a 2 solution situation. And then we could do it where there's no solutions. So in a situation like this, for the record, like, I don't even think I could dive off the side of the pool that well. So I might be a linear situation if I were trying to dive, just straight down. So as you can see, it didn't give us any information about the height or comparison with each other. So if I were to ask you this question on a test, just draw me a picture that would represent that. My drawing might be very different than Madison's drawing, might be different than Tack's drawing, like, we'll all have different drawings. And they'd all be 100% correct.
Do you have to have points labeled for a question like this?
The only points that it gave me was the 1 and 3 meters. So I'd want to make sure that those things were labeled just to indicate.
So like put 0, 1, and 0, 3.
Yeah, I don't think you'd need points labeled for these unless I specifically ask for it.
Miss Kelly,
Yeah.
what if you had like a parabola where the one of the arms was intersecting with the other arms?
Like this one?
Like one was opening up and one was opening down, but their arms were like perfectly aligned. Could you have that?
So we're going back up here. So one's opening up.
One's opening up and one's opening down, but their arms are like
It wouldn't
on
happen.
each other.
It wouldn't happen. They'd cross each other. They wouldn't line up exactly.
Okay.
Because although they might be increasing the width at the same rate, they would be doing it in two different directions. So, but by the time they intersect, it would only happen at one point.
Okay.
Because remember that these are going to get wider and wider and wider as they go. They don't stay at a constant rate. So these ones will get wider and wider and wider as they go. So really, there's never going to be a point where they lay flat directly on top of each other. That's a terrible parabola drawing, just for the record. Okay, so pretty easy stuff, right? So this is all kind of like the theory behind it. Now let's get to the meat and potatoes of it. Realize that I should have picked a different pen because you can see right through this. You can, okay. Picking some different pens so I can maybe not. Okay, so what kind of system do I have here?
Linear.
Okay, but remember that a system has two things in it. So you told it's a linear quadratic, right? So
Yes.
so we have linear because that's represented by this system right here. So when I asked what type of system it is, I want both. And this one, because it has a degree of 2, means it's a quadratic. Everybody with me? So if I ask what type of system, I'm asking for it's the linear quadratic. It's just what type of equations are you dealing with? Okay, big breath in. We're gonna be okay. So I'm looking at this and I don't like any of it. I'm used to graphing. I'm used to graphing y equals something, right? So what I'm going to do is I'm going to rearrange both these equations. Now I will tell you, ladies and gentlemen, you can leave it exactly like this and go to a table of values. Okay? Table of values will never lead you wrong, but I do want to state a word of warning here. You probably need to know where your vertex is before you do your table of values. Okay? So what I'm going to go ahead and do, and because these equations aren't nice, I'm going to go ahead and I'm going to rearrange them. So I'm going to move that y to the other side. And some of you might not even like that. Some of you may say, oh no, y's always go on the left-hand side. And I'm okay with that. Okay, so if I move the y in this one, what happens? It becomes negative. So I gotta move everything else this time. So this one's gonna be y equals negative x squared plus 6x minus 3. Okay, all right. So now that we got them to a way that I feel comfortable with them, let's go ahead and graph them. I'm gonna work in my parabola first because this one's pretty straightforward. I got a y-intercept of 1. I've got a slope of 1. I've got a y-intercept of negative 3, but I don't know where my vertex is in this. So I'm gonna work this one first before I start graphing because I wanna know where all my points are before things get crazy. Okay. So what do you guys wanna do here? Do you want to factor? Do you wanna complete the square? What do you wanna do?
Factor if we can.
Factor if we can, okay. So if I look at the factors of positive 3 that add up to 6. Okay, we're finding the vertex. Okay, we can find the vertex first. Okay, we'll find the vertex first. Do you want to complete the square or secret formula this? Secret formula? Okay, so x is equal to a negative 6 over 2 times negative 1. So x is equal to positive 3. You guys would agree with me? Did I do my math right? So then I'm going to substitute in for y. So I have negative 9 plus 18 minus 3. So y is equal to 6. So my vertex occurs
What
at...
what is that last part?
I had to substitute it in to get my y-intercept value.
What?
Or not my y-intercept, my y-coordinate of the vertex.
Wait. I don't get what you just did.
I substituted 3 into this equation everywhere I saw an x.
Oh, you skipped a step.
Yep. I only got a little bit of room. All right, so which way does this graph open? The parabola, which way does it open? Up or down? Down, because of that negative in front there. Okay,
Wait,
so
if you square something, will it become positive?
yeah, but the negative's on the outside. So I square the 3 gives me 9. 9 times negative 1 is my negative 9. Because this is like saying negative 1 times by x squared. That's what that means. So I'm going to have negative 1 times 3 squared. So negative 1 times 9 gives me my negative 9. The negative is not attached to the x. If it was, it would have to be in brackets. Okay, all right. Whew. Got to do some math. Math is hard. I don't think we can either. Did you do your quadratic solver?
Yes, ma'am.
So we know that there's going to be x-intercepts, right? You would agree with me? Are x-intercepts crucial to this graph? Like they definitely are to a reciprocal graph, and they definitely are to an absolute value graph, but they're not here because we don't know where it's going to intersect, right? The x-intercepts aren't crucial. So I know that I can't factor that, so the x-intercepts aren't easy. So I think I'm going to pop to a table of values. So remember, I'm just working on my quadratic right now. So I'm going to do a table of values for my quadratic. I always put my vertex in the middle of that. So I'm going to pick points to the left of the vertex and to the right of the vertex. So 2, 1, and 0, 4, 5, and 6. I got that one. All right, so now we got to start doing some math. So we're going to substitute 1 into the quadratic equation. So this is going to be negative 1 plus 6 is 5. 5 minus 3 is 2. Good job, everybody. Negative 4 plus 12. So 8. 8 minus 3 is 5. Now, if I've done all my math correctly, and that was a lot of mental math for me to do all at once this early in the morning. If I've done my mental math correctly, we know that it's symmetrical and it should be the exact same, but I don't trust my math. So we've got negative 16 plus 24. 8. 8 minus 3 is? Okay, so maybe I did do my math correctly. So I'm going to work smarter, not harder. And now I've got a table of values, knowing that that point here is my vertex. Okay, so that was chapter 3, right? Like everybody can do this off chapter 3. And again, the reason why I didn't go to graphing my x-intercepts is because I can't factor this. They're not nice. And I'm going to need some coordinate pairs anyway. Okay, so now we got a graph. Oh, goodness gracious, we got a graph. So 1, 2, 3, 4, 5, 6. Can I double that? 1, 2, 3, 4, 5. Yeah, maybe I can do that. So I'm gonna skip every other one. You guys can judge me if you want, but that's what I'm gonna do. Okay, make sure you have your positive negatives on there too. Okay, so let's go ahead and graph that parabola. So oh, that's not gonna work. I gotta change my y-axis. Let's go tens. So each tick there, so that's 1, 2, 3, 4, 5, 6. Okay, just so, because I need a vertex of 6. So over 3, up to 6, there's my vertex. I know I'm opening down, so at 1, I'm at 2. At 2, I'm at 5. At 4, I'm at 5. Ooh, and at 0, I'm at negative 3. 3, and at 5, I'm at 2. Now it's 6. 6 is obviously off the graph. Oh, look at that. I'm going to connect my dots. It's probably the nicest parabola I'm going to draw all year. Okay, all right, so there's my parabola. I get an extra point on the left-hand side. That's okay. You can still see the shape of the parabola. Everybody agrees with me that's a parabola, right? I like it. I don't even wait for you guys to respond. I just steamroll on.
Where are these notes gonna be posted? On Google Classroom or
Nope,
Student
all
Connect?
your notes are always on Student Connect. The only thing I've asked for you guys to do on Google Classroom is to submit your problem sets there. And your quiz, of course.
Okay.
Okay, so now we got our parabola. Now I want to graph this thing here. So let's do a table of values for this. I like table of values for graphing, finding solutions, because we know where the point is. I don't know. I don't know where to start with this one. I would start with some points that are in this table of values. So let's graph all these points and see if, so 0, 1, 2, 3, 4, 5, 6. This shouldn't be hard. It's just one more than x. So this is going to be 1, 2, 3, 4, 5, 6, 7. All right. Let's see what we got here. We got 0 and 1, 1 and 2. Anybody else excited about that? I just graphed it. It's on the parabola, so I know I have a solution right there. That's exciting. 2 and 3, 3 and 4. I don't know where my lines went in this thing. 4 and 5. Ooh, I'm super excited. 5 and 6. Okay, so because I used a table of values, and I'm going to be honest with you, table of values is usually not what I go to because it takes a little bit longer. But in this one, it's important because I need to know where those coordinate pairs are that are the solution. So before I'm done graphing here, I have two graphs on the same coordinate plane. What do I need to do? I need to label them, and then I need to label points, right? So before I state my solutions, this one is y equals x plus 1. This one is y equals negative x squared plus 6x minus 3. I'll label this point, which is 0 and negative 3, and I'll label this point, which is 3 and 6. Okay, there's my two blue. Now I'm going to do my red. So I'm going to label 0 and 1. I'm going to label 3, 3 and 4. Okay, so again, using different colors is kind of helpful. Just make sure it's clearly labeled what point belongs to what graph. We have not found the solution to this system yet, though. Okay, so we need to make a statement about the solution. So where do these cross? Here.
1 and 2 and 4 and 5.
Okay.
When we're labeling the two graphs and like the solution has to be like this one, what if we just labeled like
You totally can label just the
and then
solutions.
that counts as all of them?
Yep. Working smarter, not harder. I like it. So you need to have this. You need to state what the solutions are. Does that make sense to everybody? So I find that a table of values is a little bit better because when I graph things off like x-intercepts and just a vertex here, I'm not going to get the accuracy to see where that linear crosses exactly. All right. Everybody feel good about that? Sorta, kinda? All right. Okay, okay. For the record, this should be 3 and that should be 4. Counting is hard, because this one was example 3, down here. Example 2 was this one and example 3 was down here. Oh, they should be 4 and 5. See, counting's hard. Counting's way harder than I had hoped. Okay. All right. Here we go. Like I said, I'm going to rearrange these equations because I'm used to graphing them with a y equals. Luckily, I'm using an erasable pen. So all I did was move the y out and the 35 in, and I changed those two signs on that. And so I'm going to do the exact same thing for this one. So this is going to be 2x squared minus 8x plus 11 equals y. So what type of system is this? This is a quadratic, right? So my type Can everybody see that ink okay? It's a thinner pen. Do you want me to switch? I can switch, but it's switching to a non-erasable one, which is a commitment. Okay, so the first thing I'm going to do here is I'm going to call this quadratic 1, quadratic 2, just because they're both quadratics, like the other one was a little bit. So I'm going to work in quadratic 1 for a second. So y equals 2x squared minus 16x plus 35. Okay, I'm going to find the vertex. So I should probably do that. So x is equal to positive 16 over 2 times 2. So x is equal to 4. And now I'm going to substitute that back in. And I'm going to use my handy dandy calculator because I don't have a ton of room. So I didn't show you the math, I did it on my calculator, okay? So my vertex is 4, 3. Now in this case, I do know where my y-intercept is, but it's at 35. I'm not gonna probably end up graphing that point. Just because you know it doesn't mean you need to use it. Does that make sense to everybody? So let's go ahead and do a table of values for this parabola. And again, I'm gonna drop.
Are we supposed to find the y?
I did.
Like, okay, you just gave it to us?
I just did it in my calculator.
How?
In my calculator.
Oh.
I did the math in my calculator.
You cut out.
I did the math in my calculator.
Okay.
There's not a ton of room here, so I just didn't want to write out all the steps. You guys know how to substitute. So I trust that you guys will be good. So we're going to pick some points on the left-hand side and the right-hand side of that vertex. And again, I always plot my vertex in the middle of that table to remind myself to pick points on either side of it. And it should be symmetrical. So to the left of 4 is 3 and 2. And to the right is 5 and 6. Now we may not have enough points here, but at least this will get my graph down on the page and I'll get to see it. Okay, so I'm using my handy dandy calculator again. I'm gonna substitute in 2 in for x. So that's gonna give me 11. That's gonna be 5. Do you guys trust my math? I'm not sure you guys should trust my math. Okay, I'm gonna assume that all those are there. All right. Okay. I'm gonna go ahead and look. I'm gonna go ahead. Can I just flip back to that front one there? To that first one? I mean, when we graphed it, we saw visually that the two solutions were there and there, but could you see them in the table? Right, they're the points shared in the table. So before I go ahead and graph, I'm going to do my other parabola, just so I need to know if I gotta do more points and things like that. So it's a little bit of a guessing game. I like to get down the information that I know, and then go from there. So 2x squared minus 8x plus 11. So the x coordinate of my vertex Alright, so my vertex is at 2, 3 for this parabola. And I'm just going to drop my table of values down here. Just because I'm going to run into the quadrant 3 there. So 2, 3. So to the left of that is going to be 1 and 0. To the right of it is going to be 3 and 4. Ooh, I can do 0 really easily. I like that. I like when I can do it easily. Okay, if I substitute 1 in, 2 minus 8, negative 6, so that's going to be 5. If I put 3 in here, whew, things are fogging up. Wearing glasses is no fun. So this will be 5 here, and I'm going to guess this is 11. Okay, so looking at this, do you guys see a point of intersection?
Yes.
3 and 5. Okay, so everybody sees that this and this are a point of intersection. So I know I have at least one. So now I'm going to lay my graphs down on the graph to see if there's another one or something that there might be. Maybe if I went further, there might be. They're the same width, which is kind of cool. Did you guys notice that? They're the same width, 2 and 2. So they're going to be narrower than the regular y equals x squared. So all the stuff that you know about parabolas, you kind of have to put into play to this unit. Okay, vertexes are at 4 and 3 and 2 and 3. And I got to go up to 5. And they're both opening up. Okay, so these are all things I'm thinking about before I lay my, my increments down. So I think I'm going to use the tens again. I think that makes me feel the most comfortable. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I did it right. It's the same graph as the one above, so. All right, purple. I'm going to graph my purple graph first. So I've got 4. So 1, 2, 3, 4. Up 3. 1, 2, 3. There's my vertex. And now I'm going to plot my points. So I'm at 3 and 5. And 5 and 5. And then I'm at 2 and 11. So I'm just off the graph here a little bit. I'm going to put those points just so I can see them. All right, I'm not getting any awards for that being a great parabola. 2x minus 16x plus 35. So I'm just going to go ahead and label that right away, just so I don't get confused. Okay, so my next one, my blue one, my vertex was at 2 and 3. And I had a a point at 0 and 11, so that was up there. 1 and 5, which was here. And guys, I screwed up on a point. This is what happens when I don't break them in. 1, 2, 3, 4, 5. Did you guys see my point screw up? Yeah? So my vertex, I went over 4, up 3. And then my next point should have been at 5, 5. So that point should have been here and here, not these ones. So my graph should be like that. And this is why you do it in pencil. That's my lesson for today. That's why you do it in pencil. Okay, so now I'm going to go 3, 5. So there's my point. And I got another point here just off. There we go. Now that's looking better. Make sure I got smooth curves at the bottom. So this one's going to be y equals 2x squared minus 8x plus 11. So what do you guys notice? If they're the same width, will we have a second solution? No, because they're going to keep increasing at the same distance, right? They're going to be running almost parallel at this point. So these will never get closer together because they are the same width. They're going to be expanding. So we only have one solution here. Before I write my solution, I'm going to make sure I've got my points labeled. So I got 2, 3, and we'll do this one here, which is 1 and 5. And then on this one, I'll do my vertex, which is 4, 3. And this one over here, which is 5 and 5. Okay, so now I gotta write a statement about the solution. I only have one this time, so the solution is at 3, 5. And that's my answer to that.